with this background on the complete response, which is the forced response plus the natural response, let us get started with second order circuits. So first order circuit is what? Any circuit that is governed by a first order differential equation. In the same way, second order circuit would be any circuit that is governed by a second order differential equation. And in general, first order circuits can be simplified into what? A network that will contain what? Only one energy storage element. Second order circuits are those circuits that can be simplified into what? A network that will contain only two energy storage elements. Yes or no? First order circuit, ultimately there will be one energy storage element. Second order circuits, there will be two energy storage elements. Okay. So second order circuits. So mainly there are two types of second order circuits. One is what? The parallel RLC. The other one is what? Series RLC networks. Okay. So the first one is what? This network. Look at this network. R, L and C. All three are in parallel. So this is called as what? A parallel RLC network. And the other second order circuit that we are going to study is what? This R, L, C in series. You understood? This is what? A series RLC circuit. This one is what? A parallel RLC network. So these are the two special second order circuits that we are going to study as part of this topic. Okay. But in general, if any circuit contains what? Two energy storage elements, it need not always be one inductor and one capacitor. In these two networks, the two energy storage elements are not the same type of element. One is what? Inductor, the other one is what? Capacitor. Here also one energy storage element is what? Inductor, another energy storage element is what? Capacitor. But in general, the two energy storage elements can be anything. You can also have two capacitors, C1 and C2. It is also going to be a second order circuit. You can also have two inductors in the circuit, L1 and L2, which cannot be clubbed into what? A single inductor and so on. Then even that circuit will be what? A second order circuit. Yes, but we are not going to focus on second order circuits containing two capacitors or second order circuits containing two inductors. We will only focus on second order circuits which contain one inductor and one capacitor, and that too there will be two possibilities. The two energy storage elements can be in parallel, or the two energy storage elements can be in series. Parallel RLC and series RLC networks is what that we are going to discuss from now onwards. Okay. So first is what? The parallel RLC network. So first is what? The parallel RLC network. So already parallel RLC, it means what? R, L, C, all three will be in parallel. R, L, C. In parallel, what will be same for all the elements? In parallel, voltage will be same for the resistor, inductor and the capacitor. Let Vc be the voltage across the cap. Let us try to form a differential equation for this network in terms of Vc. Let's form the differential equation governing this parallel RLC network in terms of Vc, which is the voltage across the cap. But it is not just the voltage across the cap, it is also a drop across what? Inductor. It is also the drop across the resistor, because all three are in parallel. Okay. Now, what is this IC? It is the current through the capacitor. What is this IL? It is the current through the inductor. What is this IR? It is the current through the resistor. What is IC in terms of VC? It Is it not C dVc by dt? What is IL in terms of the voltage across the inductor? Remember, the voltage across inductor is also what? Vc. What is the current through the inductor in terms of voltage across the inductor? Voltage, how is it related to current for an inductor? V is what? L di by dt. So obviously the current must be equal to what? Integration of voltage. Yes or no? IL is equal to what? 1 by L integral V dt, Vc dt plus IL of 0, assuming we are doing the integration from 0 to t. And IR is what? The current through the resistor. Current through the resistor will again be voltage drop divided by resistance, which is nothing but Ohm's law. So it is what? Vc divided by R. So IC is what? C dVc by dt. IL is what? 1 by L integral Vc dt plus some constant of integration, which can be the initial current through the inductor, that is what? IL of 0 plus the current, not plus, the current through the resistor is what? Vc by R. Now what is the relation between the three currents? What is the relation between the three currents? How many nodes are there in this circuit? Only two nodes, right? This entire thing at the top is what? One node. This entire thing at the bottom is what? Another node. All three elements are in parallel between the same two nodes. So let us write KCL at this node. Let us write KCL at the top node. How many currents are flowing at the top node? Three currents are flowing. IC is what? Leaving. IL is leaving. IR is also leaving. No current is what? Entering. So what is KCL at this node? Tell me. IC plus IL plus IR equal to what? 0. So writing KCL at this node will give us what? IC plus IL plus IR equal to what? 0. I hope it is clear up to this point. Nothing great. We just have the parallel RLC circuit. Voltage will be same for all the elements. Let that voltage be Vc. And we are trying to form a differential equation in terms of what? Vc. We just expressed all the three currents in terms of what? Vc. Then we wrote KCL at this point. Nothing more. So IC. What is IC? What is IC? C dVc by dt. What is IL? 1 by L integral Vc of t dt plus IL of 0 plus IR. IR is what? Vc by R, and this sum is equal to what? 0. You understood? So this is the differential equation governing this parallel RLC circuit. First of all, it is not purely a differential equation because it not only contains a derivative term, it also contains some integration term. In that case, it should be called as what? Integro differential equation. This is not exactly a differential equation. It is what? An integro differential equation. Now to convert this integro differential equation into a proper differential equation, let us differentiate both sides with respect to time. Let us differentiate both sides with respect to time. When you do that, what will happen to C dVc by dt if you differentiate this with respect to time? Will it not become C times d square Vc by dt square? And what is the derivative of the second term? 1 by L integral Vc dt differentiated with respect to time. You know, dt and dt will get cancelled. Even the integration will go away. So will it not be simply Vc divided by L? IL of 0 is what? It's the initial current through the inductor. Is it not a constant? Yes or no? In any given circuit, the initial current through the inductor will have some value which is what? A constant. So IL of 0 is what? Constant. So derivative of any constant is what? 0. So d by dt of IL of 0 is what? 0. Now look at the last term, Vc by R. What is its derivative? Is it not 1 by R dVc by dt plus 1 by R dvc by dt equal to what? 0. That's all. Now we have the proper differential equation governing this parallel RLC network. C times d square vc by dt square plus vc by L plus 1 by R dvc by dt equal to what? 0. What I will do, I will multiply both sides with 1 by C. I will multiply both sides with 1 by C. Right hand side is what? 0. 0 multiplied with anything is what? 0. But left hand side, if you multiply it with 1 by C, C and 1 by C will get cancelled. You know, will it not be d square vc by dt square plus 1 by rc dvc by dt plus vc by lc equal to 0? Yes. That's all. This is the final form of the differential equation governing this parallel RLC circuit. So what kind of equation is this? Is it not a linear second order differential equation? Yes or no? Is it not a linear second order differential equation? Because it is what? A linear second order differential equation. Even our parallel RLC circuit should be called as what? Second order circuit. RC circuit is what? First order circuit. Because for RC circuit, what was that equation? RC dvc by dt plus vc equal to what? 0. And now we have what? Second order differential equation. Even the circuit should be called as what? A second order circuit. Now from the differential equation, you should form the characteristic equation. Why should you form the characteristic equation? Because roots of the characteristic equation are nothing but the poles of the circuit. And the poles will decide the form of the natural or the transient response. You understood? Yes. Anyway, how do you form the characteristic equation? Is it not by assuming a solution to this differential equation as what? A times e power st. So what is that differential equation? d square vc by dt square plus 1 by rc dvc by dt plus vc by lc equal to what? 0. Now for this differential equation, the solution that we should assume is what? Assume vc equal to what? A times e power st, which is some exponential, which is some complex exponential, a times e power st. If vc is what? Assumed to be a times e power st, then you know dvc by dt, will it not be as times e power st? Yes or no? Just differentiate this with respect to time. dvc by dt will be what? As times e power st. Once again you differentiate this with respect to time, will it not become d square vc by dt square is equal to a square times e power st? And now what? You go back to the differential equation. In place of d square vc by dt square, you write a square times e power st. Then the second term is what? First we have 1 by rc times dvc by dt. What is dvc by dt? It is as times e power st. And then you have the third term, vc divided by lc. What is vc? Assumed to be a times e power st, a times e power st divided by lc equal to what? 0. Now in this equation on the left hand side, what is common to all the three terms? What is common to all the three terms? Is it not a times e power st? If you take out a times e power st as what? Common, then what will be left on the left hand side? Take out a times e power st, want to get s square plus s divided by rc plus 1 by lc equal to what? 0. I told you whatever is the polynomial multiplying this a times e power st, and if that polynomial is equal to what, 0, then you get the characteristic equation, because a times e power st is not 0. It is what, a solution, and we are looking for a non-zero solution, which means this a times e power st is obviously not going to be 0. So if this is not 0, the only way the left hand side will be 0 is when this multiplying factor becomes what, 0. So now we are going to get the characteristic equation. So what is the characteristic equation? S square plus s by rc plus 1 by lc equal to what, 0. S square plus s by rc plus 1 by lc equal to what, 0. So is it not a second degree polynomial? S square, right? So it is what, a second degree. How many roots will be there for this equation? Is it not a quadratic equation? There will be what, 2 roots, and those 2 roots are nothing but the 2 poles of the system. Nth order system will have what, n number of poles. First order circuit will have what, 1 pole, and for a first order circuit that pole is always at s equal to what, minus 1 by tau. But for a second order circuit there will be what, 2 poles, and those 2 poles are nothing but the 2 roots of this characteristic equation, which is a quadratic equation. Is it not? In the standard form of a quadratic equation, ax square plus bx plus, say, just for reference, let me write it, ax square plus bx plus c equal to what, 0. So what is a? 1. What is b? 1 by rc. What is c? 1 by lc. And you know, for ax square plus bx plus c, the 2 roots of the equation are what? Minus b plus or minus square root of, you know, the determinant, which is b square minus 4 ac divided by 2a. Let us use the same result to write down the 2 roots of this characteristic equation, which are also going to be the 2 poles of our parallel RLC circuit. Okay. So what are the 2 poles or the 2 roots of the characteristic equation? Minus b. b is what? 1 by rc. So minus b is what? Minus 1 by rc. And then plus or minus square root of b square minus 4 ac. Again b is what? 1 by rc. b square is what? 1 by rc square minus 4 ac. a is what? 1. c is what? 1 by lc. 4 ac is what? 4 by lc minus 4 by lc divided by 2a. Again a is what? 1. So it is just 2. Now this can be written as what? Minus 1 by 2 rc, because this 2 will divide the minus 1 by rc term. It will become what? Minus 1 by 2 rc, and then plus or minus, you see, 1 by 2, if it goes inside the root, will it not become 1 by 4? Yes or no? 1 by 2, if it goes inside the root, it becomes what? 1 by 4. 1 by 4 into 1 by rc whole square, is it not 1 by 2 rc whole square? So inside the root, the first term can be written as what? 1 by 2 rc whole square minus, you say again 1 by 2, when it goes inside the root, it becomes what? 1 by 4. 1 by 4 into 4 is what? 1. And this 1 by lc, I'll write it as what? 1 by root lc square. Okay, 1 by lc, because 4 and 4 will get cancelled. I'm going to write it as 1 by root lc square. That's all. These are the 2 roots of our characteristic equation. Please copy this down, all of you. Minus 1 by 2 rc plus or minus square root of 1 by 2 rc whole square minus 1 by root lc squared. You understood? Yes. Minus 1 by 2 rc plus or minus square root of 1 by 2 rc squared minus 1 by root lc squared. Okay. Let's go to the next slide. So the two roots of the characteristic equation, in other words, the two poles of the circuit, let us denote them by S1, 2. S1 and S2 are what? The two poles of the system. So S1, 2 are what? The two poles of the system. Okay. So what is this S1, 2? Minus 1 by 2 RC plus or minus square root of 1 by 2 RC squared minus 1 by root LC squared. Now let us define two new terms. Let us define two new terms. The first term is what? Alpha. What is this alpha? Defined as 1 by 2 RC. Alpha is called as what? The exponential decaying coefficient. So when we look at the actual form of the natural response, you will understand why alpha is called as the exponential decaying coefficient. Okay. Alpha is called as what? Exponential decaying coefficient. The other term that we are going to define is called as what? Omega naught. This omega naught is what? The resonance frequency, and it is what? 1 by square root LC. This omega naught is what? Resonance frequency. So what are the two new factors? One is alpha, which is called as what? The exponential decaying coefficient, and alpha is equal to what? 1 by 2 RC. And the other one is what? Omega naught, which is called the resonance frequency of the network, and it is equal to what? 1 by root LC. These two factors are extremely important. For a parallel RLC circuit, alpha is what? 1 by 2 RC. Omega naught is what? 1 by root LC. Alpha is what? 1 by 2 RC. Omega naught is what? 1 by square root LC. Okay. Now if you come back to the expression for the two roots of the characteristic equation, which also happen to be what? The poles of the system, minus 1 by 2 RC. What is 1 by 2 RC for us? Is it not alpha? So this minus 1 by 2 RC, is it not minus alpha? Yes. And then we have what? Plus minus square root of, inside the square root, the first term is what? 1 by 2 RC squared. Again 1 by 2 RC is what? Alpha. So 1 by 2 RC squared is what? Alpha squared. Minus 1 by root LC squared. 1 by root LC is what? Omega naught. 1 by root LC squared is what? Omega naught squared. Okay. So what are the two roots of the characteristic equation? Minus alpha plus or minus square root of alpha squared minus omega naught square. Is it not easy to remember? It is quite simple to remember. But before that, you should remember that alpha is what? 1 by 2 RC, and omega naught is what? 1 by root LC. Then always for a parallel RLC circuit, the two poles of the system are going to be minus alpha plus or minus square root of alpha square minus omega naught square. Okay. Now we are going to have three cases. First, let me outline the three cases. Then we'll look at what is the natural response in each case. Okay. See. Number one, alpha is what? Greater than omega naught. If alpha is what? Greater than omega naught, then the natural response, it is what? Said to be over damped. If alpha is what? Greater than omega naught, then the natural response or the transient response is said to be over damped. Number two, is what? Alpha equal to omega naught. Number 2 is what? Alpha equal to omega naught. In this case, the natural response is said to be critically damped. When alpha is what? More than omega naught, natural response is said to be overdamped. And when alpha is equal to omega naught, the natural response is said to be critically damped. Okay. Well, if you ask me what is the meaning of the word damped, damped is related to what? Damping. Damped is related to what? The amount of damping in the circuit. And what is damping related to? Damping is what? Related to energy dissipation in the circuit. If there is lot of energy dissipation in the circuit, then you have more damping. If you have very little energy dissipation in the circuit, then you have very little damping. So just keep in mind, damping is what? Related to energy dissipation in any system. If the energy gets dissipated very fast or very quickly, then there is a lot of damping. If there is very little damping, then the energy will not get dissipated that fast. It will stay in the system for quite some time. If there is what? Very little damping. I hope the notion of damping is clear. So damping is related to what? Energy dissipation in the system or circuit. More the energy dissipation, more the amount of damping. Okay. What is the third possibility? Alpha can be less than omega naught. If alpha is what? Less than omega naught, then the same natural response is said to be under damped. Alpha greater than omega naught, what is the natural response? It is over damped. And if alpha is what? Less than omega naught, then the same natural response is said to be under damped. That's all. In any second order circuit, these are the three types of natural responses one can expect. In any second order circuit, these are the three types of natural responses that we can expect. One is what? Overdamped response. Next is what? Critically damped natural response. Last one is what? An underdamped natural response. And we get overdamped when alpha is what? More than omega naught. And we get underdamped when alpha is what? Less than omega naught. And very rarely it happens that alpha is equal to what? Omega naught. And in that case, the natural response is what? Said to be critically damped. But if you take any real system, always the natural response will be what? Either overdamped or underdamped. Because for it to be critically damped, alpha must be exactly equal to what? Omega naught. That means 1 by 2 RC must be exactly equal to what? 1 by root LC. Yes or no? For alpha to be equal to omega naught, this 1 by 2 RC should be exactly equal to what? 1 by square root LC. So it is never possible to set the component value such that 1 by 2 RC is exactly equal to what? 1 by root LC. Even if you try to do that, even if you pick components whose values are such that 1 by 2 RC becomes equal to what? 1 by root LC. Remember, all components will have a thermal drift, and also there will be some tolerance for every component value. If you pick a 1 kilo ohm resistor, it is not exactly a 1 kilo ohm resistor. There will be some slight error in the value of the resistance. And also the value of the component, be it what? Inductance or resistance, it will vary with temperature. So at some point in time, maybe 1 by 2 RC will become equal to what? 1 by root LC. But after some time, due to what? A change in temperature in the neighborhood, the values of R, L and C will get modified a bit, such that alpha will not be equal to what? Omega naught. In that case, the natural response is not going to be critically damped. So in reality, you will never get a critically damped natural response. Always you will get either overdamped or underdamped. You understood? But critically damped is what? The boundary between overdamped and underdamped. Okay? So what is the first form of the natural response? natural response is said to be what? Over damped. So first is what? Over damped natural response. First of all, when you get this overdamped natural response, when alpha is what? Greater than omega naught. What are the two roots of the characteristic equation? Minus alpha plus or minus square root of alpha square minus omega naught squared. If alpha is what? Greater than omega naught, does it not mean alpha square will be greater than omega naught square? Alpha square more than omega naught square. Alpha square minus omega naught square, will it not be positive? Square root of anything positive, will it not be real? Square root of anything negative is what? Imaginary. Square root of anything positive is what? Real. For example, square root of 4. Square root of 4 is what? Either 2 or minus 2. Already we have plus or minus. You can simply say square root of 4 is what? 2. Then it will be what? Minus alpha plus or minus square root 4, which will be minus alpha plus or minus 2. You understood? So when alpha is what? Greater than omega naught, the determinant alpha square minus omega naught square is going to be positive. Square root of anything positive will be what? Real. Alpha is what? 1 by 2 RC. Minus alpha is what? Minus 1 by 2 RC. That is also what? Real. Real plus or minus real will also be what? A real number. Yes. So when alpha is what? Greater than omega naught, the two poles are going to be negative real. The two poles are going to be negative real. You can easily verify it. Both the poles will be what? Lying on the negative real axis. Okay. So S1 comma 2, both roots are negative real and distinct. Both the poles or both the roots of the characteristic equation are going to be negative real and distinct. Okay. Negative real and distinct, it means what? Again, if there is what? The complex plane, the two poles will be like this. Okay. This is what? P1, this is what? P2. You can see both the poles are not identical and they lie on what? The negative real axis. Okay. In fact, let me call them S1 and S2. Sorry. S1, S2. You can see both the poles are going to be what? Negative real and distinct. Now the question is, what is the form of the natural response when the natural response is what? Overdamped. The form of the natural response is what? A1 e power S1t plus A2 e power S2t. A1 e power S1t plus A2 e power S2t. This is the natural response when the natural response is what? Overdamped. What is S1? It is one root of the equation. S2 is what? The other root of the characteristic equation. How many unknowns are there in the expression for the natural response? A1 and A2. But you know, our circuit also contains what? Two energy storage elements, and both the energy storage elements will have what? Their own initial condition. In fact, the circuit we have is what? The parallel RLC network. What are the two initial conditions in a parallel RLC network? First is what? The initial current through the inductor. Second is what? The initial voltage across the capacitor. So from those two initial conditions, we should be able to solve for A1 and A2. But before you solve for A1 and A2 using what? The two given initial conditions, you should add the steady state response to this natural response to get the complete response. Always remember, complete response is what? Steady state response plus natural response. So to this natural response, you add the steady state response, then you use the initial conditions to find these two unknowns, that is what? A1 and A2. I hope it is clear. I am just giving you an overview of what you should expect when the natural response is what? Over damped. So natural response when it is what? Over damped will be the form a1 e power s1t plus a2 e power s2t. And the two poles are going to be what? Distinct, and also they will lie on the negative real axis. Okay. What is the second type of natural response? It is what? Critically damped natural response. When do you get this critically damped natural response? Is it not when alpha is equal to omega naught? It is when alpha is equal to what? Omega naught. Once again, what is the general expression for S1 comma 2? That is the two roots of the characteristic equation. Is it not this? Minus alpha plus or minus square root of alpha squared minus omega naught square. And right now, alpha is equal to what? Omega naught. If alpha is equal to omega naught, alpha square will be equal to what? Omega naught square. Then alpha square minus omega naught square, will it not be 0? Square root of 0 is what? 0. So what are the two roots going to be? Both the roots are going to be what? Identical, and be equal to what? Minus alpha. Alpha is what? 1 by 2 RC, which is real. Minus alpha, would it not be negative real? So are we not having two repeated roots? We are having what? Two repeated roots or two repeated poles. So both the poles are exactly at the same location. At what location? At minus alpha. Again, minus alpha is what? Negative real. So here, in case of critically damped natural response, the two roots are, so the two roots or the two poles are going to be what? Negative real and identical. Earlier, over damped case, the two roots are what? Negative real and distinct. Yes. But now the two poles are going to be what? Negative real and identical. And what is the form of the natural response when it is over, not over, critically damped? What is the form of the natural response when the natural response is what? Critically damped? It is this thing, e power minus alpha t times a1t plus a2. Again, you get this result from the theory of ordinary differential equations. You get this result from the theory of what? Differential equations. E power minus alpha t times a1t plus a2. Again, alpha is what? 1 by 2 RC. So from the given values of R, L and C, you can compute what? The value of alpha. But the two unknowns here are what? A1 and A2. Once again, you add the steady state response to this natural response to get the complete response. You make use of what? The two initial conditions. Initial current through inductor, initial voltage across cap, and solve for A1 and A2. Yes. So for overdamped case, what is the form of the natural response? A1 e power S1t plus A2 e power S2t, where S1 and S2 are what? The two poles or the two roots of the characteristic equation. And in case of critically damped natural response, it is of the form e power minus alpha t times A1t plus A2. Now the last remaining natural response is what? The underdamped, natural response. What is it? Underdamped natural response. So when do you get this underdamped natural response? Is it not when alpha is less than omega naught? You will get this underdamped natural response when alpha is what? Less than omega naught. Okay. Once again, let us start by writing the expression for the two poles, that is S1 comma 2, which is minus alpha plus or minus square root of alpha square minus omega naught square. If alpha is what? Less than omega naught, even alpha square will be what? Less than omega naught square. If alpha square is what? Less than omega naught square, then this alpha square minus omega naught square, will it not be negative? Alpha less than omega naught. Alpha square minus omega naught square will be what? Some negative number. Now square root of anything negative, is it not imaginary? For example, square root of minus 2 or square root of minus 4, is it not j2? Yes or no? Square root of minus 4 is what? Square root of minus 1 into square root of 4. Square root of minus 1 is what? J. Square root of 4 is what? 2. So it is what? j2 square root of minus 4. So in the same way, alpha square minus omega naught square, because it is going to be negative, even this square root will be what? An imaginary number. So this time what are the two roots going to be? Are they not going to be complex conjugate? Yes. Okay, before we express the two roots as what? Complex conjugate poles, let me modify this a bit. This can be written as what? Minus alpha plus or minus square root of minus 1 times omega naught square minus alpha square. This can again be written as what? Minus alpha plus or minus. I'll write square root minus 1 separately, then I'll write square root of omega naught square minus alpha square. What is the square root minus 1? It is nothing but j. Then we have what? Square root of omega naught square minus alpha square. Now we will define a frequency called as what? Omega d. This omega d is what? The natural resonance frequency. Omega naught is what? Just the resonance frequency. Omega d is what? The natural resonance frequency. Okay. So omega d is what? The natural resonance frequency. And what is this omega d? Equal to square root of omega naught square minus alpha square. Remember, this omega d, that is what? The natural resonance frequency, comes into the picture only when the natural response is what? Underdamped. For overdamped and critically damped, there is nothing like a natural resonance frequency. It comes into play only when the natural response is what? Underdamped. And what is omega d? Square root of omega naught square minus alpha square. Omega d, is it not real? It is real, because alpha is what? Less than omega naught. It is same as what? Omega naught greater than alpha. Omega naught more than alpha. Omega naught square minus alpha square will be what? Positive. Square root of anything positive will be what? Real. So omega d is what? Real. Okay. Now come back to this. Minus alpha plus or minus. What is square root minus 1? J. And we define omega d as what? We defined this square root of omega naught square minus alpha square as what? Omega d. Then in place of this I can just write omega d. That's all. Minus alpha plus or minus j omega d. They are the two roots of the characteristic equation, or the two poles. What are the two poles? Separately, one pole is what? Minus alpha plus j omega d. The other pole is what? Minus alpha minus j omega d. So minus alpha plus j omega d and minus alpha minus j omega d, are they not complex conjugate of each other? Yes. So what is the real part of both the poles? Minus alpha, which is what? Negative real. So the two poles will lie on what? The left half plane. Of course, they are what? Complex conjugate. So on the complex plane, the two poles will be like this. You understood? So there is what? Like minus alpha, there is what? J omega d. This is what? Minus j omega d. So there is what? S1. There is what? S2. So as you can see, both the poles are complex conjugate. Okay. Now the final point of this discussion is what? What is the form of the natural response when it is underdamped? When the natural response is what? Underdamped, it is of the form e power minus alpha t. It is of the form e power minus alpha t times a1 cos omega dt plus a2 sin omega dt. That's all. This is the form of the natural response. When the natural response is what? Under damped. E power minus alpha t times a1 cos omega dt plus a2 sin omega dt. a1 cos omega dt plus a2 sin omega dt. If you want, you can combine both the terms. Are they not at the same frequency of how much? Omega d. Yes, if you want, you can combine both the terms into what? A single cosine term or single sine term. Okay, and write it as what? E power minus alpha t times some a times cos of omega dt plus phi. You understood? Yes. So what do you understand from this expression for the underdamped natural response? It is what? Going to be oscillatory. Sine function or cosine function, will it not be oscillatory? But then what is the amplitude of the oscillation? This e power minus alpha t times a, is it not the amplitude of the oscillation? And look at the amplitude. Is it constant amplitude or amplitude will decay with time? Amplitude is what? A into e power minus alpha t. E power minus alpha t, is it not a decaying exponential? So here the amplitude of the oscillations will decay with time. So the transient or the natural response will be what? Something like this, where you can see the amplitude, it will continuously decay with time. After a long time, the amplitude will decay to what? 0. Then the natural response will die out, or the transient response will die out, so that only the steady state response will remain at t equal to what? Infinity. Understood? So in which case, you get an oscillatory transient response only for underdamped case. The natural response is what? Going to be oscillatory, and it oscillates at what frequency? It oscillates at a frequency of what? Omega d. So you can use either this expression or the second expression. If you look at the first expression, there are two unknowns a1 and a2, which can be found from the two initial conditions. Even if you look at the second expression, which contains only one cosine term, still there are what? Two unknowns in the form of what? Capital A and also phi. So to find the values of A and phi, again you should make use of what? The two initial conditions: initial current through inductor, initial voltage across capacitor. So the point is what? Very simple. Whenever you come across a parallel RLC circuit, first you should decide whether the natural response is going to be overdamped or critically damped or underdamped. And for that, you just have to find the values of alpha and omega naught. Alpha is what? 1 by 2 RC. Omega naught is what? 1 by square root LC. So once you get the values of alpha and omega naught, by comparing alpha with omega naught, we can immediately decide whether natural response is what? Overdamped or critically damped or underdamped. Write down the corresponding form of the natural response. Then you add forced response or the steady state response to the natural response. And then using the initial conditions, you evaluate the values of the various unknowns, mainly what? A1 and A2. So this is the kind of approach that we are going to take for second order circuits. Yes. So today I have just given an overview of second order circuits. Tomorrow we'll start looking at the actual second order circuits, and we'll try to directly write any voltage or any current in a second order circuit without doing much. So without putting much effort, we will be able to directly write expression for any voltage or any current as a function of time in a second order circuit, which we will do tomorrow. I'll see you tomorrow. Bye.